day to you. In the last week, we were discussing about the chapter number 4. We basically discussed about the material derivative, and based on that, we discussed the Reynolds transport theorem. Hopefully you have gone through the relevant problems which I assigned you during the week, and they should be clear to you. If you have any question from the previous week, any confusion, any query, let me discuss
No,
that, otherwise we'll move on to the next topic. Okay, if it is clear, quickly let me know about the Reynolds transport theorem. What's the mathematical statement for the Reynolds transport theorem? Quickly.
dB system over dt is equal to dB control volume
The
over
total
dt.
derivative of the system property,
Yes, sir.
that's d by dt of the system, should be equal to the time rate of change of the property
Of control volume.
within the control volume, that is partial by partial t, triple integral. I'm writing it as a single integral, but it's a triple integral.
Rho b
into
dv
dv plus the property coming into the control volume and going out of the control volume, the net property flow. This control surface integral into rho b v dot n. Sorry for the bad n. N is the unit vector. It's the normal vector, normal area vector, unit vector of the normal vector that is perpendicular to the area. So is this statement clear?
Yes, sir.
So today we are going to start chapter number 5, which is the finite control volume analysis. And that chapter is wholly solely based on the understanding of the Reynolds transport theorem. So we'll be discussing the finite control volume analysis. And this is wholly solely based on this Reynolds transport theorem. If I ask you, or if I draw a system here, let's say this blue rectangle is a system. What's the quality of this system? How you will define that it is a system? What will make it a system and not a control volume?
Sir, move करें.
Control volume can also move.
Okay.
We discussed in the last chapter that control volume can be a moving. So what quality will make it a system? What property will make the system?
Sir, it is fixed.
It is fixed. So control volume can also be a fixed.
Sir, but at a time that the control volume will move after some time.
No, it will not move. If it's a fixed control volume or a stationary body, the control volume will not move. What's the quality of a system we discussed in the last lecture?
ये actual है और वो control volume imaginary है?
No. The revise नहीं करते आप लोग. The mass of the system is constant, right? The Lagrange approach. ऐसा ही है?
Yes, sir.
So if I represent the mass of the system as m system, then with time, what should happen to the mass of the system?
Constant रहेगा.
Sir, it
Means
remains
that
same.
time rate of change of the mass of the system would be equal to
0.
0.
0. That is d by dt of the system mass is equal to 0. What it is representing? It is representing the system, and it's basically the, now this term is representing what? That capital B, which property we're discussing now, is the mass. So capital B of the system is equal to the mass of the system. So small b would be equal to
unit b over mass,
which is basically 1, right?
unit, yes.
So if I write the expanded form of this term, the Reynolds transport theorem, what would that form be? It would be partial by partial t integral control volume rho. Now b is 1, so I will not be writing here. dv plus integral control surface rho v dot and should be equal to 0, right? This is called the continuity equation. Clear?
Yes, sir.
So what continuity equation is telling is that with time rate, there should be nothing stored or released by the control volume. That is, there should be nothing happening inside the control volume. The control volume should not release any mass, nor it should store any mass, right? The first term, that
Yes,
with
sir.
time, the control volume should not be acting as a sink and it should not be acting as a source. It should be a neutral entity. It should not add mass to the system or it should not absorb mass from the system. And the other term, that is the convective term, it's telling us that the net mass flow should be 0. That is, the mass entering into the control volume should be equal to the mass going out. Then our system will be a system. Then we can define it as a system. Then the mass will remain fixed. Then the time rate of change of the mass should remain equal to 0, right?
Yes, sir.
Now, if I say that my system is a steady state system, so what will happen to the equation?
Sir, first term will become 0.
The first term will be 0, so only will be left with this term, integral control surface rho v dot n dA equal to 0, right? And if I say my
Yes, sir.
system is, or the fluid for which I'm considering this continuity equation is incompressible, then what will happen to the equation?
There will be no
Density
change
by
in.
The density will be constant, it will take an outside and then we can take it to the other side, so it will be eliminated from the equation, right? So integral control
Yes, sir.
surface v dot n d k equals to 0. And now if I say that the area over which I am applying this integral is a constant area, then what would happen to this equation? That the area of the inlet and the outlet is constant, it's fixed. So we will not need this v dot n, we will not need this integral, we will need that minus v in, that is the total inlet area velocity into area inlet plus velocity out, that is total outflow velocity into the total area going out from which the flow is going out, right? This should be equal to 0, or in other words, A out V out should be equal to A in into V in, or the volume. This is basically what? Volume flow rate, right? So the volume coming out from the control volume should be equal to the volume flow rate into the control volume. Or if it's incompressible flow, I can multiply with density on both sides. That will not affect my equation. Is equal to rho Q in, that is rho into volume flow rate is mass flow rate, so m dot out should be equal to m dot in, that is for steady state. So this is the continuity equation for a system that is experiencing steady state flow, and the fluid is incompressible and the area is fixed. So it is the most simplified form of the continuity equation which you have been studying your whole life, and this is the most generalized form of the continuity equation, which is considering all the factors that can happen inside a control volume. Clear?
Yes, sir.
Any question in this?
Nope, sir.
Okay, if it is clear, then we move on. Sorry, I have lost track. So we solve some problems to have better understanding of the continuity equation and to apply it to different problem situations, how we can get different information by applying the same continuity equation. So in the first problem, you are seeing a water hydrant that is connected to a nozzle for a fire hose. The problem requires you that you need to calculate the flow rate at point 1, that is at this location. That is at this location at the inlet. If you require a velocity of 20 meter per second at the location 2, that is the outlet of the nozzle at this point. So can we do that? Can we get the mass flow rate if we know the velocity at the outlet?
Yes, sir.
It is also given to you that
Sir, A1 B1 equals to into B2. No.
it is also defined to you that the flow is incompressible. Now, my suggestion is to you that you will see that the area is constant, right? At both the sections, at section 1 and section 2, right? And also it is given to you that the flow is incompressible. You can directly jump to the conclusion that the volume flow rate at point 2 should be equal to the volume flow rate at point.
Serious, sir? ये area 2 at point 2 में area small नहीं हो जाता sir? Or like
Yes, but for the outlet it is fixed.
Okay sir.
सर ये एरिया कांस्टेंट का मतलब ये है कि वो आउटलेट की मतलब एरिया चेंज नहीं हो रहा फ्लो की वजह से या किसी और वजह से.
ऐसे ही. Just give me a minute. So we were discussing that we know that the area at both inlet and the outlet is fixed and the flow is incompressible. So we can directly apply Q2 equals to Q1, right? And is that we start from the scratch. That is, we start from the general continuity equation. हम थोड़ी देर के लिए इसको भूल जाते हैं कि हमें ये चीज पता है. And we just start from the general continuity equation and apply all the simplification so that we can have the concept, okay, what's happening, why we are eliminating terms. So if I ask you to write the general equation of continuity, that would be partial by partial t integral control volume rho dv plus integral control surface rho v dot and dA equals to 0, right?
Yes.
Now, what simplification we can do?
So first term will become 0 due to steady flow.
First term would be 0 because we are having steady flow. right? So we'll be left with the second term only, that is integral control surface rho v dot n dA equals to 0. Fine. Now
Yes, sir.
we know that we have two points of flow, that is the section 1 and the section 2. Section 1 will act as inlet, so we can write that because it's a constant area section. So for that we'll write that minus for the inlet rho 1, that is density at the point 1, that is the area of the point 1, into v1, that is the velocity at point 1, plus at section 2 we have, let's say, density as rho 2, for plus sign because it's an outlet, into a2 into v2, it should be equal to 0. Now we can eliminate the density from this problem. Why? Because it is allowed that we can assume this flow to be incompressible. So we can write that rho 1 equals to rho 2. So if rho 1 is equals to rho 2, because the flow is incompressible, then we'll only be left with that a2 v2 equals to a1 v1, right?
Yes, sir. Yes, sir.
Or we can write a1 v1 as q1. So we'll get the volume flow rate at the section 1 with the help of the parameters of the section 2, a2 v2. Can you calculate the volume flow rate? Because we know the area, we know the velocity. It's a circular cross section having diameter 40 millimeters and the velocity is 20 meter per second. So what the flow rate would be, q1 would be,
So t squared by 4 multiplied by.
so you need to run the calculator now, number crunching. You will need to multiply 20 with pi 3.14 into t square, that is 40 exponential minus 3 square divided by 4. It comes out to be 0.025 meter cube per second.
Yes, sir.
And now you need to calculate the mass flow rate at point. How will you calculate the mass flow rate?
So density multiplied.
You will simple multiply the m dot 1 would be equal to density into q1, and density of the water is 1000, so we'll simply multiply it with 1000. So that would be 1000 multiplied by the answer, it's 25.12 units would be kg per second. So is it clear? Any question in this problem?
एक्सक्यूज मी सर
सर आप
सर एक
Yes.
क्वेश्चन था सर एक क्वेश्चन था कि अगर इस केस में तो हमारे पास वो कंट्रोल वॉल्यूम वाली टर्म तो जीरो हो जाती है। लेट्स से हमारे पास एक फनल है या कोई स्टोरेज टैंक है, उसमें हम वाटर डिप करते हैं, तो फिर उसमें तो ये जो कंट्रोल वॉल्यूम वाली टर्म है, जिसे अनस्टेडी टर्म कह रहे हैं आप, वो तो जीरो नहीं होगी?
The control volume term would only be zero when we will considering unsteady flows. If we are considering the steady flow, that is, there is no change in the properties of the flow, that is not storing some mass or nor it is releasing some mass. Let's try to discuss this concept. What's the first time representing? Let's say this is a control volume. Flow is entering from this side and is leaving from this side. If it's a steady state flow, then this, according to continuity equation, this inlet should be equal to the m1 should be equal to m2, right?
Yes sir.
But if I say there are two chemicals inside the control volume, that is, I have placed, let's say, sodium inside here, and from here I am pumping water. What will happen? There will be a chemical reaction inside the control volume.
Yes sir.
So water will be converting into something else. Let's say it's converted into I don't know what's the reaction between water and sodium. Let's say it's NaOH. We get sodium hydroxide. So on the outlet will not get any water. Will get some byproduct, right?
Yes, sir.
The mass of that byproduct will be less than that is coming in, right?
Yes, sir. Yes, sir. Yes, sir. ठीक है.
It means that control volume is storing some mass. There are
Yes,
some
sir.
unsteady effects involved here. With time, this mass is changing. Clear?
Yes, sir. Clear. Okay. Thank you, sir.
Any question else? कोई और चीज समझना है you? Okay, if it's clear, then we move to the next problem. This is a very similar problem. We will be applying this to relate the velocity, the question of that, how if the area is variable, how you will deal with that problem, how the continuity equation will be modified. So we just do this problem. In this problem, you have incompressible laminar steady flow that develops in a straight pipe. Initially, at section 1, the velocity of the flow is constant, that is, it is uniform velocity, and the velocity is equal to capital U at section 1. U1 is equal to U. But as the flow progresses, we see that the velocity is a variable. It's changing with the radius of the pipe. At the center, it is minimum, and at the center it is maximum, and at the pipe surface it is minimum equal to 0. So it means that the velocity is changing with the area. And why it is 0 at the surface pipe section? Why? And why it is maximum at the center?
Friction वगैरह रहती है.
Due to the no slip condition, right? The layers at the boundaries of the pipe will face no slip condition. They will attach themselves to the pipe surface. So at their velocity will be 0 and it will be maximum. The layers beneath that will be facing less friction, and that's why the velocity will be maximum at the center. Now you are asked to relate the velocity at the pipe inlet, that is U, with the maximum velocity at the section 2. How can you relate that?
So we will apply the equation.
We write the continuity equation, that is partial by partial T integral control volume rho dV plus integral control surface rho V dA should be 0. And from the problem statement, we know that the flow is laminar steady flow. So it means the first term would be 0.
0.
So we'll be only left with the second term, that is control surface integral rho V dot M dA equals to 0. Now if we see that we have two surfaces, we have two control surfaces. If this is the control volume, this blue line, this blue dashed line representing your control volume. And if we see the control volume, we see that we have two surfaces. One is the inlet, that is section 1 is acting as inlet, and the section 2 is acting as outlet. At section 1, the velocity is fixed and the area is also fixed, right?
Yes, sir.
So we can write the integral or this integral at the inlet as minus rho A1 into U1, which is basically capital U, right? But at section 2, we see that the velocity is maximum at the center, but it is minimum by relationship of the velocity with the area. So we cannot write this simple integral. We need to write it as integral at control surface outlet as rho u2 is given to us, which is given to us as a function. We can eliminate this n because we have already decided that it's an outlet. So we don't need to write the n now, the dot product, into dA2 should be equal to 0. Is this clear?
Yes, sir.
Yes.
Now answer my just a little question. If this is a circle, let's assume it's a circle. Let me draw a circle. If this is a circle, and I say this is its center, what's the area of the center?
सर आपकी स्क्रीन थोड़ी लैग होके आ रही है.
स्क्रीन स्टॉक है. जी सर,
Give me a few seconds.
सर सेंटर का
What is
Sir,
the
आ गया.
area of the center?
सर वो तो पॉइंट
Yes.
होगा, उसका एरिया तो 0 होगा.
Negligible.
This point.
Negligible.
0.
It would be 0. We can approximate it as 0. If I say that the radius of the circle is capital R, then what would you say that the area of this region is?
Pi r square.
pi r square.
Pi r
Pi, very good.
delta
Pi r square. Okay. Then I draw another circle inside it. Is the red circle visible to you?
No, sir.
No, sir.
Yes, sir. Visible.
And I say the area of this red circle is small r. Sorry, the radius of this red circle is small r. What's its area?
Pi small r
circle
square.
का small r square.
Pi small r square. Okay. If I say the distance between these two circles is variable, that is the small r can also change. Capital R will remain fixed. Small r can vary from 0 to capital R, right? And that change is represented by dr. So now what's the area of the region between the two circles? The area of the donut.
Pi r2 square minus r1 square.
But if I say that small r is varying,
सर फिर उसके लिए आ जाएगा pi r dr.
Pi r
for
dr.
that you will need the circumference of the boundary, right? The outer circle. That is 2 pi r, right?
Yes.
And multiply that boundary with the change in radius, that is dr, right?
Yes.
So this will be the region of the donut between the two circles. And this, if I say this area is equal to dA2. तो अब एरिया वेरिएबल हो गया ना?
Yes, sir.
So the velocity function given to us is a function of r, right? Here we can see that u2 is a function of r. And we have also made our area function of r. So we can now write that minus, because density is a constant in both cases, it's incompressible, so we can take it to the other side, so we don't need to write it. We'll just write a1 u, sorry, plus integral from 0 to capital R u2, यहाँ पे आप उसका फंक्शन लिख लेंगे, ठीक है, u2 का, into 2 dA2 is now 2 pi r into dr. Clear?
Yes, sir.
This is just short mistake here. We should be writing it as 2 pi r, and this can maximum go to capital R. Okay. Can you solve this integral? You will just need to put this u2 function here, this function here, and you can then solve this. When you solve this integral, you will get the relationship. Okay.
सर u2 का फंक्शन क्या है?
That is u max into 1 minus r by r square.
Okay.
It's given in the problem. Okay. When you solve this, you will get this relationship that u max is 2 times of the inlet velocity u. That is, it is 2 times the inlet velocity u. Is it clear? Any problem or any question in regards to this?
सर फर्स्ट वाले का एरिया पाया स्क्वायर है ना?
Yes.
Okay.
Is it clear?
जैसे ये जो आपने पहली क्वेश्चन लाइन सर इंटरवल को एक्सप्लेन कर दे दोबारा सर को नजर नहीं आ रहा
Which equation? This equation?
माइनस a1u into प्लस
Okay. This integral which I am highlighting in blue. यहाँ से आगे आप बात कर रहे हैं, right?
नो सर ऊपर से कर रहा हूँ जहाँ पे वो आपने कहा था कि सरफेस पे वेलोसिटी कम होगी और सेंटर में ज्यादा होगी यहाँ पे d(a2) क्या
And this one. Okay, I just summarize the problem for you. We're given a steady state laminar flow and we are asked to relate the velocity at the inlet, that is this u, with the maximum velocity that is at the center of this outlet. And we know that the velocity at the center is maximum because there is no slip condition. At the surface, the flow is attached to the pipe, so there is no slip condition, the velocity becomes 0 and it is maximum at the center because the center line here faces the minimum resistance. Because the flow is steady, that's why we have eliminated the first term and we are only left with the second term of the continuity equation, that is the integral of the control surface rho v dot n dA should be equal to 0. When we see the control surfaces, we see that we have two control surfaces. One is this section 1 here. This is the control surface. We see that it's a constant control surface and velocity is constant also. So we can simply write it as rho a1u and we see that it's an inlet to the control volume. So there will be a negative sign with it. We see that the second control surface is a function of the radius and the velocity is also a function of the radius. So we need to solve it in the integral form. So we inspect the area. We see that how the area is varying with radius r. We develop that function here and then we write the velocity function and we solve this. After solving, we get to know that the maximum velocity is related 2 times to the inlet velocity. Clear?
Yes, sir. Okay.
It's clear. Then we solve another problem. We'll be solving a lot of problems today, so you can have a better concept of the continuity equation. Some of the problems I will just be describing to you and you'll be solving them yourselves. Others we will be solving in detail. Okay, here in this problem, we have a Y mixer. Y mixer is basically like जैसे आप अपने घर में गर्म पानी और ठंडे पानी को खोलते हैं तो फिर वो मिक्स होके एक एवरेज पानी आता है आपके पास शॉवर में, तो Y mixer इसी तरह की चीज है. But in this Y mixer, we are mixing water and alcohol. We have water in the one side at a volume flow rate of 0.1 meter cube per second. And we have alcohol having specific gravity 0.8 at a flow rate of 0.3 meter cube per second. After mixing, you will get a mixture of water and alcohol. The question is asking you to calculate the average density of the mixture. That is the mixture of alcohol and water. Can you solve this?
Yes, sir.
We define a control volume like this. And we say this is the 1, this is the 2 region, and outlet is the third control surface. So there are two inlets and one outlet in this problem. We know that according to the continuity equation, if this flow is incompressible, Q1 plus Q2 should be equal to
Q3.
Q3, and we know Q1 and Q2, right?
Yes,
So
sir.
Q3 should be equal to 0.4 meter cube per second.
Yes, sir.
And if this flow is incompressible, also the mass flow rate should be
Equal.
so m dot 1 plus m dot 2 should be equal to m dot 3, right? Or row 1 q1 plus row 2 q2 should be equal to row 3 q3. Clear?
Yes, sir.
Yes, sir.
So in this equation we know all the terms except the row 3. सिर्फ हमें row 3 unknown है, and we know all other terms. That is, we know row 1, we know q1, we know row 2, we know q2, and we know q3. So when we'll solve this, we'll get the density of the mixture. That is row 3. Clear?
Yes.
Any problem in this?
सर यहाँ पे हमें कहा था कि ये हमारे पास स्टेडी फ्लो कंडीशन है.
Sometimes you will have to assume, right? If it is not
Okay.
given, the problem is asking you to calculate the average density. So for average density, you will have to assume two things. That is, one, this flow is steady flow. If this is not a steady flow, then you cannot calculate the average property, because the property will be changing with time. The density will change every instant the water and alcohol mixes, right? So if it's the average density, then you can have that it's a steady flow. This average density term is telling you that you can assume it as a steady flow. And if you don't assume it incompressible, then you cannot write this second equation. Then you need to know the density functions, because the problem has stated the water density as 999 kg per meter cube, and it has given you the specific gravity of the alcohol. So you can calculate the rho alcohol will be equal to the specific gravity into rho of water. So if density of the water is fixed, and if density of the alcohol is fixed, it means that you can assume it as incompressible flow. Clear?
Yes, sir.
And you need to write you need assumptions. Whatever you assume, you need. Okay, I will just give you a hint to solve these problems, and then you will solve yourself. In the next problem, you are given a water jet pump. A water jet pump is like just a syringe. Syringe का तो पता है ना, suppose में कोई तो नहीं, syringe क्या होती है, ठीक है? Injection. So it's just like an injection. So what's happened in a water jet pump, when you push the plunger in, the center line fluid, it gets accelerated, it moves a faster velocity as compared to the fluid on the sides. So in this problem, you are required to calculate the entrained fluid flow rate, that is the flow rate of this fluid that is here in this region, here and here. When you're given the velocity of the center fluid, that is 30 meter per second, and when you're given the velocity of the fluid at the outlet, that is 6 meter per second. Can you do that?
सर इसमें हम 3 surfaces consider करेंगे. ये जो
Yes, you will consider 3 surfaces like this. This would be your one surface. Then this will be your second surface. This is your
सर
second
आपकी
surface.
स्क्रीन हाँ जी सही अब
This
नजर आ
is
रही.
one surface, and this would be your third surface. Clear? You are
Yes.
given the area of the third surface. इसका area given है, velocity given है. You are given the area of the second surface and the velocity. You can calculate the area of the first surface would be equal to the area of the third surface minus area of the second surface, right?
Yes, sir.
So we know that the volume flow rate should be equal to, that is Q1 plus Q2 should be equal to
Q3.
Q3. You can calculate Q3, you can calculate Q2, you will get Q1, which is the required. Okay, you will just need to have some unit conversion, because the answer required is in liter per second, and you will get the answer in meter cube per second. Is it clear?
Yes.
Yes, sir.
Now the next problem is a very interesting one. It's the last problem we're going to solve today. In the next problem, you have a air compressor. देखा होगा सबने एयर कंप्रेसर? Are you all familiar with the air compressors?
Yes, sir.
गाड़ी के
Yes,
टायर में
sir.
हवा भरवाने जाते
Yes,
हैं
sir.
तो आपको
Yes,
नजर आता
sir.
हो, ठीक है? In this air compressor we have, and just quickly discuss this and solve this. What's happening? The air compressor is taking in air at 10 feet cube per second, and the density of the inlet air is 0.00238 slugs per feet cube. The volume of this tank is 20 feet cube per second, and the outlet is 1.2 inches in diameter, and the velocity of the air coming out from it is 700 feet per second, and the density is 0.0035 slugs per feet cube. The density is increased. Now, the problem is asking, determine the rate in slugs per second at which the mass of air in the tank is increasing or decreasing. Because you can see that there is an inlet, there is an outlet, but the density is changing. It means that the mass of the tank will be filled. The tank has to fill a volume of what? 20 feet cube. So is the mass increasing in the tank or decreasing? If these are the conditions. So how will you calculate this?
सर हम कंटिन्यूटी इक्वेशन अप्लाई करेंगे फिर और
We'll write this form. We'll write, yes, we will apply the continuity equation. We'll say that if this is a steady state system, and if this is a continuous system, if the continuity equation is applicable, then the time rate of change of mass should be equal to 0, which means that dm system by dt, which we can calculate. Now we can say that, okay, there is some mass coming in, right? The difference of the mass coming in and mass coming out should be 0 if it's a constant system. So if we can calculate this difference, we can tell that either the mass is increasing, either the mass is decreasing, or the mass is constant. If it is 0, we'll see that there is no increase in mass, no decrease in mass. It's a constant system. It's a proper system. But if there is if this result is positive, it means that the mass is
Increasing.
Yes, and if this result is negative, it means that the mass is
Decreasing.
decreasing. Okay. Can you calculate m dot in? You are given.
Sir, row A1, V1.
Yes, you are given row 1. You are given Q1, right? This section and
Yes,
inlet
sir.
section. If
Yes,
this is
sir.
the section
Yeah.
1. This is the section 1. Can you calculate m dot out? This is the section 2 here. Can you calculate?
Row 2, A2.
Yes,
you
sir.
are
वो
given
A1 और A2 और V2.
a row 2, A2, and V2. Just keep in mind that the area should be in feet square. The diameter here is in inches. Convert it into feet. Convert this diameter into feet and then calculate the area. Okay.
Yes, sir.
So when you will calculate, you will get the time rate of change of mass. Okay, you can do this on your own. Now the second part. Determine the average time rate of change of air density within the tank. अब हम ये देख रहे हैं कि at the inlet the density is less and at the outlet the density is increased, right?
Yes, sir.
Yes,
So in the second part, the problem is asking you, what is the time rate of change of density? Density किस rate से change हो रही है, किस rate से vary कर रही है? So can you calculate that?
सर उसके लिए टाइम होगा ना, मतलब कि मास फ्लो जो है उसमें जितना चेंज होगा उससे हम टाइम फाइंड कर लेंगे.
Yes.
सर हमारे पास जो
उसकी
We have
बेसिस पे
calculated- Yes, we have calculated this term, right? dm system by dt. Right? We know this term now
यस सर
from
वो
this
उस पे
calculation.
यस सर.
And if I write it like this, that mass of the system is basically combination of two parameters. Which parameters?
सर रो इनटू वॉल्यूम.
Density into volume, right?
Yes, sir.
And we see that the volume of the tank is fixed. It cannot change. It is fixed at
20 feet
40
cube.
feet cube. Yes, if it is fixed, it means that it is constant, right? So from this derivative, we can take the volume outside, and we will get d by dt rho. So did we get the time rate change of density?
Yes, sir.
Yes sir, volume बस divide कर देंगे.
So d rho by dt is basically equal to dm system divided by dt, and this whole divided by the volume of the tank. Clear?
Yes sir.
Any question in this problem? Any question, any query?
No, sir.
These are your homework problems. You need to solve these. These are very interesting problems. You can see that all the problems we have solved today are giving you a new dimension. You're getting a new result from each problem. You can get, so all these problems are different problems. So you should solve them. I believe you will be able to solve them. Maybe you get to know a new point, or you may have some question in regards that something that you don't understand. Maybe you get some problem that is involving the unsteady terms. So how to equate that? Or maybe you get a problem that is involving much more complex integrals, how to solve that. So you should solve those, and we can discuss them in the next class. Okay.
Okay, sir.
Okay, sir.
Now there is just because in the next topic we'll be having a moving control volume. So I just want to give you an idea of the moving control volume, and then we are going to end this. What's the moving control volume? Because practically speaking, most of the times as a mechanical engineer, you will be encountering the bodies in motion, right?
Yes.
Yes, sir.
Yes, sir.
Statics will not be a major part. So if I say this is some vehicle and this is moving with velocity v, and I ask you to calculate if this is the fuel tank of this vehicle, and I ask you to apply the continuity equation or the momentum equation on the fuel tank. That's what's coming into the fuel tank and what's going out from the fuel tank. How the rate of the fuel is changing. Let's say this is the vehicles out, and this. So you will see that when the vehicle is moving with velocity v, the control volume will also move with velocity v, right? Let's say the
Yes, sir.
velocity of the control volume is vcv and the velocity of the vehicle is v. But now the control volume is moving. So how to tackle that problem? For this, we need to have the observer perspective. From an observer that is sitting in the vehicle. Let's say there is an observer here, observer A. From his perspective, the control volume is fixed, right?
Stationary, sir.
From another observer, which is standing, let's say observer B, which is standing on road, from his perspective, the vehicle is moving and the control volume is also moving, right?
Yes, sir.
So these are two velocities that are from the perspective of an observer that is fixed, right? These are the absolute velocities. If the observer is fixed, right?
Yes, sir.
But let's say we have another observer C, which is sitting on another vehicle and is also moving. Then what will be the concept utilized here?
Relative velocity.
Relative, sir.
Yes, you will see that if the observer C is moving with velocity, let's say v2, then the velocity would be the relative velocity would be equal to V control volume or V minus V2, right?
V2.
So the control volume would be moving with the velocity W. Clear?
Yes, sir.
Yes, sir.
So we need to measure the velocities from the perspective of a fixed observer, and then we see that how this control volume is moving with respect to a moving observer, and then we calculate the relative velocity. Clear? Because most of the time in fluid mechanics, what would be happening? Let's say if this is a jet engine. From an observer perspective who is sitting on the aeroplane, it's stationary, right?
Yes, sir.
From an observer on ground, this jet engine would be moving with the velocity of the plane, right?
Yes, sir.
Yes, sir.
But in actuality, the fluid coming into it would be
Right side.
in the opposing direction, having its own velocity.
Yes, sir.
So the control volume will be moving with the velocity that would be difference of the, or the sum of these two, right? Velocity of the plane minus V, right?
Right,
The
sir.
fluid would be entering the control volume with this relative velocity, right?
Yes, sir.
So is the concept of the moving control volume clear?
Yes, sir.
But remember, this control volume is also fixed. It's moving, but it's non-deformable. It's not a deforming control volume. It's non-deformable. It's still non-deformable. But what will we do now in all the equation, instead of using the absolute velocity V, now we'll be using this relative velocity W in the continuity equation or any subsequent equation for which we are experiencing the control volume that is moving. Okay. If the control volume is fixed, we'll be using the normal V, this V. But if the control volume is moving, then we'll be using the relative velocity. Depending upon the situation, we'll calculate that relative velocity. Any question?
Sir, ये जो relative velocity है fluid की है with respect
The
to wind.
the velocity of the control volume with respect to the fluid.
Fluid, ठीक है.
प्रैक्टिकली हमें तब ज्यादा क्लियर होगी जब हम प्रॉब्लम सॉल्व करेंगे मूविंग कंट्रोल वॉल्यूम के, बिकॉज अभी तो मैं आपको सिर्फ सेंस दे रहा हूँ कि अच्छा रिलेटिव वेलोसिटी कैलकुलेट क्यों हो रही है, और प्रैक्टिकली हमारी जो अंडरस्टैंडिंग है वो ज्यादा बेहतर तब बनेगी जब हम कोई प्रॉब्लम सॉल्व करेंगे, बिकॉज वी आर हैविंग 3 वेलोसिटीज इन दिस केस. The control volume velocity from a stationary point of reference, which I have already explained, the absolute fluid velocity observed from a stationary point of reference, right? And the relative velocity, that is the difference between the two velocities. They can be adding or they can be subtracting. So that relative velocity will be calculated based on case to case. Clear?